see. Just explain here my name, so it's Jorge Kondo, but that's one more. I have 3 names, so that's another one. So Masayuki Kondo, that's fine, or George, whatever, or Douglas. You can call me. There's many names for that. I would like to thank you, the organizers, for inviting me for this talk, of course. And I would apologize already, because basically the title is Optical Bistability Noise Amplifier. I'm going to talk about terahertz wave radiation. I'm going to actually explain a little bit this title for narrowband terahertz real-time imaging and driven no equilibrium phase transition in a room temperature vapor cell. Okay, I'm going to explain that a bit later. The thing is, this is basically a almost free equation talk, so you can blame Tommaso after that if you want. I'm actually I've got a position from the Federal University of Santa Catarina in the south of Brazil, where I'm trying to put a lab there that's called Lab Atomo, or Atomo Lab, depends on people saying. It's actually a very nice island in the south of Brazil, and probably we can try to manage some conference there sometime. And the university is right in the middle of the island, right? So it's pretty nice, actually. But the whole work that I'm going to present here today was done in the other island, was done in UK, actually, at their university, right? So everything that I'm going to show you, we did in the GQC Center in their university, in the group of Charles Adams, by support of Brazilian and British agencies. That's it, okay. So I have two main goals here. The first one will be to present a little bit of EIT. I'm not going into details, but I'm going to try to use and show how we can use EIT, electromagnetic induced transparency, in hot vapors and atomic optical bistability to detect terahertz radiation, right? And my second goal would be actually stay on time. Let's see if that works. Okay, so a little bit of a motivation for that. So this is a paper from 2012 from Jonathan Sadlasek. So this was from the Schaefer and Timopfau, Schaefer in Oklahoma and Timopfau in Stuttgart. And they did this very nice experiment when they did this electrometry of microwave electric field. So this has a fairly simple EIT. So this is the 7/8 laser coupled in the ground, excited, and the Rydberg state. And then they couple the Rydberg state with another state with microwave, a microwave source, right? So we have this very nice EIT signal, and when you probe this outer transition, you can see the splitting of these things. It's a very simple experiment. It has just one cell, vapor cell. The blue laser and the red laser counter-propagate each other, detect here, and you can see this very nice transparency. You can, for this, measure, for example, the electric field of your microwave. And you build basically a microwave detector for that, right? So, okay, so it's a very nice experiment in 2012. And by that time, in 2012, I was in the middle of my PhD in São Carlos, University of São Paulo. And we are doing something similar to that, actually, most similar to that. So basically, I will not explain EIT again, because Sebastian already explained a lot for us, and it's going to be another talk for EIT, so I'm going to skip all that. So yeah, so basically we have a metastable state here. We're coupling to the control laser and a probe laser, and for some conditions we get this very nice transparency window on the absorption signal, right? And back at the day, so this is experimental thing, the cell. So this is exactly by the time what we were doing in our lab in Brazil, in São Carlos, for getting a EIT signal, but we were using this EIT signal just to lock in frequency our laser for excitation to Rydberg states, right? So we're building an ultra-cold experiment there in an optical MOT and an optical trap to study dipole-dipole interaction, this is long dipole-dipole interaction in population exchange and molecular potentials and stuff. And the thing is that EIT was just a small part of the entire experiment, right? So that actually, I mean, it was looked like it was a waste of a thing that we were doing there. So I mean, in this experiment, we did a lot of results. We have a lot of papers published that. I will not comment on that on this talk. Okay, good. So after that, I moved, actually I finished my PhD, I moved to Durham, actually to explore more these hot vapors in EIT, electro-induced transparency. And there, I changed the element from rubidium to cesium and started working with these vapor cells, right? And then, okay, and then they're doing already these 3-photon EIT systems. So they're observing EIT with 3-photon in cesium in hot vapor cells. But besides that, so this is a quick experiment of that. So that's the cell, has a 2 mm length. The cesium are trapped inside. And you have all this casing to heat the sample, and you have the lasers to basically observe EIT. So the thing is, if you forget now the recipe for electromagnetic transparency, and you start just pumping atoms into the Rydberg state, you're creating more and more Rydberg atoms there. When you create more and more Rydberg atoms, they start to interact. And now so this is the probe beam actually. You continue to see transparency, but it's a completely different phenomenon. So it's not coherence at all. It's just it's actually population shelving. We're pumping Rydberg states, and the beam becomes transparent to the ground, to the first excited state. And back at that time, people were doing a few modeling for that. So this is a simple Fairley model for explaining this bistability window. So you're pumping more Rydberg atoms into the system, and you're getting some asymmetry on the lines, and then you start observing this bistability breaking up of the signal, right? Yeah. So you can model with that with some optical equations, some rate equations, and you can rescale the detuning and the decaying rates in order to get at least some feeling of what is happening, right? So yeah, so we have, what I tried to do is to explain basically two main features that we are going to use to detect terahertz radiation. So there is the EIT, as the first experiment from Sadlasek, electrometry, and bistability window. And we are curious to see what happens when you show actually terahertz radiation on top of these atoms on these hot samples, hot or room temperature samples. First of all, if we want to do electrometry, of course we know that we can do it in microwave length, but actually depends on Rydberg states. You can manage. So this is the reduced dipole matrix elements for transitions between Rydberg states. I mean, it's from the 21p state. I'm not sure right now, but for potassium, rubidium, cesium. So besides this is a narrow band terahertz detector sensor. You can tune your system either by changing the element, right, for another frequency, if you need them. And basically, the thing is, so this heater we designed to be transparent to the terahertz radiation. It's a heater made of PTFE, Teflon, right, and it's transparent to terahertz radiation. See if we got a picture of that. Yeah, so there it is. This is a picture of the terahertz. It has so it has basically the optical view for the lasers and the terahertz, and you can see from the sides the fluorescence of the system. Right? So the thing is fairly simple. We have a 3-photon excitation to the Rydberg states. So where either we can, for the 3-photon, excite directly to the 21p state if you want, or either we can observe EIT configuration on this system. And we then couple the transition with the terahertz radiation, which is detuned from the first Rydberg state. And then we can actually make this Raman transition and excite directly from the ground state 20s half Rydberg states, if we need it. Right? If we go for the EIT, we can observe a nicely EIT window when we don't have terahertz radiation, so we don't couple the terahertz beam here, and we have this nice EIT window, which has about 80 megahertz of line width. And when you apply some terahertz, you can see the splitting of the state in the outer tone states, and you can measure. You can do the same electrometry than the Sadlasek was doing on that time, right? So basically, there's nothing new here. The only thing is that we can show that we can do the same thing for terahertz or millimeter wave length. What was actually interesting on this experiment was that the experiment is this. So we have we have the cesium vapor cell. These are two parabolic mirrors for the terahertz beam that has a hole in the middle that pass basically the lasers, the 3 lasers. And when you look to the side of the cell, we could see this, right? But this is not on the regime of EIT. This is the regime of high pumping. So we are pumping the system to the Rydberg atoms, and we can observe the decaying of the Rydberg states to the ground state. So we can see this fairly interesting fluorescence. In this, we can observe that there is a standing wave of the terahertz inside the cell. So basically, the terahertz pass through the cell. It reflects something inside the cell, and you get these standing waves inside the cell. And when you have Rydberg, when you have terahertz radiation, we can see this fluorescence. The idea then is that we can see these with your naked eyes, basically. So if you can calibrate some camera or a detector, right, you can actually measure in real time the intensity of the electric field of your terahertz radiation. Well, you can see this in real time, so we can actually make a movie of this, right? You can turn it on and off your Rydberg or your terahertz laser and see this changing over time. Okay. Right. So this is just analysis of that picture, one of those pictures. And the picture actually we see fluorescence from 3 main wavelengths, red, green, and blue one. These are actually the picture and the data collected from the camera. This is a camera that we got from the press office of their university. So it's not nothing sophisticated. It's very commercial, right? The idea was to create something that was very easy to use, actually. But the real thing is that when we excite Rydberg states using the terahertz, we are creating this avalanche of decaying path, right? So there's a lot of red, mostly green, and some blue lasers, some blue light getting out of the system. And then we actually calibrate the intensity of the light recorded by the camera with the EIT signal, and we can actually have this linear relation between the intensity of the recorded signal on the camera and the intensity of the terahertz beam, right? So yeah, it worked, right? That was published. So that thing, I didn't mention anything about bistability, right, on this part of the work actually, but that will become interesting now. So we made a video of that, just to show you a little bit what was happening on the lab. So we had this. Sorry, the music is not important. And I think that I cannot turn it off for some reason. Sorry, I apologize for that. Okay, so so we have this lightsaber, right? That's coming out of. So this is the glass, the quartz wall, and you can see this starting flashing up, this orange and blue states of the Rydberg states. And what was happening that we were just aligned the Rydberg, the terahertz beam on top of the other 3 beams. When we got a fairly number of atoms, we can start seeing this transition between 2 phases, the orange one and the green one. Sorry, that's British song. So just get a little bit further from this. So now the terahertz beam is actually on the perpendicular side of the cell, right? So, I mean, we can scan that if you need it. So basically, you have this live stream of the information of the terahertz beam that you can use either to make some image or image something inside the cell if you want. Okay, that's enough, I guess. Sorry. Okay, good. So you can see that that wasn't the purpose actually of this experiment. When we start seeing these flashes of orange, it's actually orange. You can see these flashing up in the cell. What's happening is that we are observing actually bistability windows there, right? We are changing basically into two meta states. The first one is the high-lying Rydberg states, which are decaying to low line to the ground states, and they are mostly green. And the low line Rydberg states are mostly red, so that's what you're seeing there. Let's see if I can explain that better. And we actually made a lot of interactive measurement on bistability window. So this is actually, there's no terahertz in here. We were just testing the stability of the system. For people that work with bistability systems, is that this is very sensible to basically everything, right? So it's hard to get a nice scanning of things, but I mean, we did that for this. And this is a 2D migrate. So this is the same, right? So this is just no transmission, transmission, and this is bistability window. And now I think I can explain the title that I chose first, which is bistability window noise amplifier. The thing is that when we're trying to make this more stable possible in order to basically explore the parameter space of the systems, we spent at least almost 2 months just figuring out what was wrong with the system that was too unstable, right? So we are just ruling out things and doing Fourier transform for the noise and see what is happening. And we are just blocking all of this noise from the experiment until we get this. And in that group meeting that we were talking with Charles Adams, if you know, then from GQC, at the end of the meeting, he said for us, looks like you built a noise amplifier. So you see, that actually didn't traumatize me at all, but so that's what I was thinking about when I choose this title. Okay, on the bistability part of things, so we have the cesium vapor. We're calling here the on state, which is the upper state, and the off state, which is the green one, which is the lower state of the Rydberg atoms, of the shelving signal. Okay, so if we see for the bistability window of these things, we can see that without the terahertz field, this is the normal bistability system. So we're scanning here the Rydberg laser, and you can see that you open up or go to up with this frequency and go down with this frequency, you open up this bistability window. When you apply the terahertz field, you actually move the entire bistability window around, actually. If you change, that depends on the frequency, right? If you change the frequency, you change to decide that these things are going to change. So what we did here was just to measure this a little bit, and this is without terahertz. You have the bistability window right here. And here, when you apply some terahertz and you start seeing that the bistability window breaks up into regions, if you force a little bit more terahertz, it breaks into different regions. And we can explore these 2 regions to do something. In this case, what we did was, so right here, the Rydberg beam is in some frequency, and we're scanning the power of the terahertz electric field, right? So if you change the amplitude, which is the intensity, you can see the bistability window on the terahertz scanning. On the theoretical part of this experiment, to understand what is happening, we bump our heads in the wall for a long time, try to figure out what is going on. Actually, we came up with a few modelings for that, based on the old model that we had from bistability. At the end, we basically gave up and we asked help for Igor Lezanov from University of Nottingham. And then he was starting to bumping his head into the wall for us, right? So basically the idea was that, I mean, besides all of those states, we have 3 main states, the ground, the Rydberg, and the terahertz states. And from particular rescaling of these parameters, the detuning and the decaying, you can actually got what we were actually observing on the experiment. And this is a plot actually from the population, if I'm not mistaken, of the Rydberg state, right? So the transparency is proportional in some way to the number of Rydberg atoms that you're exciting. Yeah, we can talk more if someone asks about that. With that, we can actually create. So if we go for the sensor side of the bistability window, we can use the bistability window shift in frequency. So we basically plot this. So this shift in the bistability window and the frequencies with the terahertz intensity, we can build this linear with intensity with the terahertz. So we can, just observing the moving of the frequency in the bistability window to get the intensity of the terahertz beam. The other thing that was pretty neat was these, actually. So exploring that parameter space that we had, so we choose here to leave the Rydberg laser on some frequency, which is between, I mean, just in the middle of these two windows of transition for some Rydberg, for some terahertz power, right? And when we go the recycling of the terahertz intensity, you just go up to the up state, and when you go down, you stay on the upper state. So what we did here was to use this to create a latching system. So basically what we have here is the terahertz being turned on for 1 millisecond, so this is second scale. So the terahertz beam is turned on for 1 millisecond, and the transmission signal gets on for how much as the lasers are stable enough for maintain this. And then we reset the system, and we can turn it off again, and reset the system, turn it off again. So we have this latching system, which is pretty neat, actually. Yeah, so we got this last year out. Just to present everything that was involved to this work, for those who knows. So this is Natalia. Natalia and Nick was mostly working on the bistability experiment, and this is Christopher Wade, which was most working on the terahertz radiation detector. This is Matteo Macuzzi and Igor Lezanovsky from the university was helping us on the theory part of the things, and Kevin and Charles from their university. And I guess that's it. Okay, we still have time, I guess.
Okay, questions?